In this video, we're going to start looking at circular motion. And so for today, we'll just look at uniform circular motion, and we will learn about centripetal acceleration and centripetal force. So for uniform circular motion, we will have an object that travels around a circle of radius r at constant speed v. First, take a look at a picture of what this looks like. So here we have a circular path, and the dot here represents our object, and this will be our starting point. And I'm just going to draw a few different points in time for where this object is located. And so let's just say that we are drawing this object at equal intervals of time. We could just say that the second position is 1 second later, and then another second later we would be here, and so on. So there are a few positions for this object, and what we want to do to start this is draw the velocity vectors at those points. And velocity is always tangent to the path that is taken. So the velocity, we could draw the velocity vectors to look like this. So there's our velocity vectors for each of those points. And even though the object is not speeding up or slowing down, we said constant speed, the velocity is changing because the object is changing directions, which means that there must be acceleration, right? If the velocity is changing, then there is some acceleration. And what we want to do is figure out what that acceleration is. And so to do that, we will first look at what the direction of that acceleration is, and then we will look at how to figure out what the magnitude of that acceleration is. Starting with direction, we know that acceleration is equal to the derivative of velocity over time, or you can think of this as the change in velocity over time if we wanted to get an average acceleration, which is good enough because we're just trying to figure out what the direction is. And so from this equation, what we can see is that the acceleration is proportional to the change in velocity, which means that acceleration will have the same direction as delta v, change in velocity. So let's go ahead and try to figure out the direction for acceleration for that first time interval. So if we look at our picture here, we want to figure out the acceleration when the object went from position 0 to position 1, from time 0 to time 1. So what is this acceleration here? And we'll call that a0. And again, we're just looking at the direction here. So what we could do here is we could take those velocity vectors, so this would be v1, for example, and this would be v0, and we could subtract those to get delta v. So for time 0 to 1, delta v is equal to v1 minus v0. And so let's go ahead and get those two vectors and subtract them. So here are the two vectors for velocity, and to subtract them, what we can do is we can take v1 and we can add it to the negative of v0. So what we're going to do is flip this vector here. So we will flip v0 so that it is facing the other direction. And now we can just add those two vectors together. And to do that, we could use the tit-to-tail method, or we could use parallelogram rule. So if I put those two vectors at the same point, the same starting point, then what we could just do is draw parallel lines. So use a dashed line here. We'll draw parallel lines for those vectors. So there's the parallel line for velocity 1, and then the parallel line for velocity 0 looks like this. And then the result of adding those vectors together is going to go from here, the starting point, to where those intersect. So let me actually use a solid line here. And so there is our velocity vector. So this is a0. And I'll go ahead and put that over here in our circle. So it looks something like this, pretty much straight to the left. Okay, so We don't know the value for that acceleration, but we do know the direction is to the left. So let's go ahead and get another time interval, and let's pick one that's a little bit further away. So we'll look at the time interval from 3 to 4. So we need these two vectors here. And we're going to subtract those just like we did in the last example. So here we have delta v is equal to the velocity at time 4 minus the velocity at time 3. So there's our two velocity vectors, and just like before, we'll take v3 and we will flip it. So if we flip velocity v3, it looks something like this. And just like before, we can draw parallel lines for each of those velocities. So the parallel line for velocity v3 would look something like this. And then the parallel line for v4 is going to look something like this. And then we can draw the result going from the start of both to the intersection of that dashed line. So that is going to be our acceleration vector, and we can call that A3. So let's draw that on our circle. So I'm just going to take this acceleration vector that we just finished, and I'm going to put that on our circle at the third time interval. And we have 2 points here. Let's go ahead and try to get one more point, and we'll look at our last time interval from time 4 to 5. So we're looking at these two velocity vectors here. So delta v here is going to be velocity 5 minus velocity 4. So what we have to do again is take velocity 4 and we need to flip this. So if we flip this, then that vector looks like this. And we will put those two together at the same point, and then we'll draw our parallel lines so that we can add those together. So here's our parallel line for velocity 4, and then here's our parallel line for velocity 5. And then we'll use a red arrow to represent the direction for acceleration, which looks like that. And then we'll just copy that over to our circle. So this one goes on the 4th velocity, v4. So our arrow looks like that. And so now we have 3 different acceleration vectors. And hopefully what you can see is that the general direction here is towards the center of the circle, right? So A0 is pointing towards the center. A3 is supposed to point towards the center. We're a little bit off. If we were to put these intervals closer together, so they're kind of spread out here, then you would get a more accurate representation of the acceleration and they would point closer to the center. But hopefully you can see that the direction for this acceleration is towards the center. So acceleration for uniform circular motion is towards the center, and this is why we call this acceleration centripetal acceleration. And we label it with a C subscript. So A sub C stands for centripetal acceleration. What about the magnitude of this acceleration? So in this video, I'm just going to give you the magnitude of the centripetal acceleration, and I'll have another video of the proof for that value. So I didn't want to make this video too long, and so there will be a separate video if you care to see the proof for it. You actually don't need to know the proof for it, but I did want to include it. It'll just be in a separate video. The magnitude for centripetal acceleration is equal to the velocity of the object squared divided by the radius of the circular path. In this case, we call that r. So altogether, centripetal acceleration is equal to v squared over r, and the direction is toward the center of the circle. So centripetal force, we label that F sub c, is equal to the mass of the object times the centripetal acceleration. and we just found that that is equal to mass times v squared over r. Any force can be the centripetal force. So for example, the moon orbiting Earth, gravity would be the centripetal force. It's the force causing the object to move in a circle. If you were to move a ball that is attached to a string in a circular path, the centripetal force in this case would be the tension force. For a roller coaster that is going around a loop, the centripetal force is towards the center, and that's a combination of the normal force and gravitational force, mg. So multiple forces can make up the centripetal force. So the centripetal force is the net force that is acting towards the center of the circle, causing that object to accelerate around a circle. In another video, I will show the proof for the acceleration equaling v squared over r, and then we will look at some examples dealing with centripetal acceleration and centripetal force.